Hello and welcome. Today I am here with another module of functionals in R. In the previous module we had some discussions about higher order functions and some specific functionals like reduce function and many more. We have also some discussions about predicates and many things. In this module we will be discussing about how the functionals are used to replace some different kinds of loops. We will be discussing about several functionals in R that are used mostly. So, let us see what is there in this module. So, here we are going to learn functionals as a replacement of for loop, the lapply, sapply, vapply and eapply functions and different types of looping. Here we are starting with the ideas of using a functional instead of using a for loop. We will try to give you a number of reasons in favor of this. Each functional is made or destined for a special object. So, when you recognize the functional, try to know immediately why it is being used. So, let us see what functional actually does. Firstly, functionals act as a replacement of for loops. It helps to reduce bugs. It is popularly used and tested. Many of the functionals are written in C and hence inherit the advantages of C. Indeed, usually you need to focus on the speed of the program, but one should look at it after sorting out other more alarming problems, which includes the correctness of the program, which is often sacrificed during the use of for loop. So, let us have a quick ideas regarding this. To deal with the problem, let us consider functionals that are often an excellent substitute of for loops. The reason behind this is they allow to deal with the objective of writing a code in a more concise manner. Sometimes functionals may even perform slightly better than its equivalent for loop. But as we have just discussed, here for now we will just concentrate on the clarity, not on the runtime of the program. So, let us start with the apply family of functions which acts as functional. The simplest member of this family of functions is the lapply function. So, let us concentrate on this. The lapply function primarily takes three arguments. The first of these would be a list. Even if it is not a list, then as we all know that it can be transformed to a list by the command as.list. Secondly, it requires a function that will be applied to each of the elements of the list, and finally some other arguments might optionally be there. Now think about what actually this function does. At the very beginning, it takes a function, applies it to other element in a list that is provided by us, and then again returns the results in the form of a list. So, let us consider how it works. For this, let us consider the empty cars dataset. As we all know, this dataset contains measurements regarding 11 components of 32 cars. Now, suppose for each of the columns we want to find the minimum value considering each and every cars. So, what do we do? Consider the code that is given here. Since the same function minimum is applied to each of the columns, so the simplest thing that we are familiar with is the use of a for loop. Here exactly we are doing that. Here I runs from 1 to 11, which is the number of column here, and hence the vector named minimum contains all the minimum values corresponding to the columns. So, this whole thing is pretty simple, but isn't it a bit elaborate? Remember, we have come across these kinds of problems in one of the previous modules as well. There also it was shown that how this method comes along with a number of errors. So, here comes the idea of the lapply function. Here, if we just put the arguments of the lapply function as x is equal to empty cards and the function that is being applied to is minimum, then the whole thing will be done. The second code is far more clear and concise than the first one, even though a vector would be preferable than a list as an output. But we can always have solutions to this problem. We are coming into this a little while later. But the other advantage of the code is the function lapply. Unlike the for loops, it does not produce any intermediate result during the execution. By this, what I mean is, in case of the for loop, the value of the result of the loop, that is a vector minimum, keeps on changing at each iteration. But the result of the function lapply is not going to produce any intermediate step, though it can be assigned to a variable. Here we can use the function unlist to convert the output from a list to a vector. Now the question is, why do we require the list representation? It is indeed very obvious. Primarily the objective of it is to make it more compact. Here in the context of this example, one thing that I need to mention is that the data frame is also a list. So we can include this as an argument of the lapply function. Now let us consider another of the similar kinds of an example. Suppose we are curious about the type of the variables that are involved in the air quality data set. In the air quality data set, we have 6 columns corresponding to the 153 rows. So what do? Here we are applying the function plus on the air quality data set, and as we know from the functionality of the lapply function, the class function is being applied to each of the columns of the air quality data frame, and then the output is obtained in the form of a list, though we can always unlist that. Now let us talk about the other two lapply family of functions, that are sapply and vapply functions. Primarily they are variants of the lapply function, as we know. Then where the difference is? Actually the difference lies within the output. If you see the outputs, then you will find that these functions produce vectors, matrices and other higher dimensional arrays instead of lists. This is unlike the lapply function, which produces list usually. Now let us have a look at the previous example. In that case, we wanted to know the types of variables which were involved in the air quality data set, and we had used lapply function in order to get that. Here we are applying the sapply function to do that, and here is our output. So now you can clearly see what the difference is. In the previous case we had a list as output, but here it is a vector that we are getting. So as we can see, this sapply function simply wraps around the lapply function. So it seems it is really great to use. Moreover, it saves a lot of typing time. So why do we need to search for anything else? Actually the sapply function have a very little control on the type of the output that they are giving. Now have a look at this code. Here when you give it an empty list, then the sapply will return another empty list. In this case, as we know, we can expect an empty logical vector, but we are getting an empty list. So as we can see, the sapply function may provide an excellent shortcut when working with R in interactive mode. But when you go for writing a serious R code, don't use this function. Then what are the alternatives? Here we have one, and this is the vapply function. This is the second variant of the lapply function. To overcome the problem created by the sapply function, the vapply function is improvised in such a way that it allows us to use one more argument through which we can fix the kind of output that we are wanting the function to return. Now let's illustrate what we are trying to say. Look at the code. Here, unlike the supply function, if you add this extra argument here, we will come up with a zero length logical vector. The apply function can provide either of the two things. It improves consistency by providing either the return type we are expecting or error. So, we are in an advantageous position now, and through this the errors can easily be captured, and hence we will come up with a more robust code. Here we are revisiting the example of finding the classes of the variables involved in the air quality data. At the very beginning, we have got a list of using the lapply function. Then using the supply function, we got a vector. Here, if we use a apply function like the one we have used here, then with this extra argument as well, we are getting the same output as we have got using the supply function. Now, the reason why we said earlier that supply function works better for interactive use is because in that case, you will have plenty of opportunities to notice if you have committed an error or not. But in case you are writing a function, or rather a complicated function, the occasions are very few which will tell you about the errors. Now suppose we are considering the list of data frames together. Here we are considering the data frame women, BOD and air quality. Here we named it as set underscore list. Now if we try to find the number of columns in each of the data frame in the list of data frames, then we just need to write supply, then set underscore list and encall as arguments, and here is the output that we are getting. So till then it is fine. Now let us move on one step further. Add an extra argument numeric 1 in course of using the apply function, and here is the output. Have a look at both the outputs. These two are the same, so no difference has been shown using the additional argument. But let us consider another data frame which contains the data frames women and quality, but also carries a null data frame. So here is our data frame that we have given here, and we are naming it as df underscore list 1. Like the previous case, if we use supply function here and use df underscore list 1 and encall as arguments, then we will get a list of numbers containing the number of columns of the data frame including the null value. But remember, in beginning we told you that supply function is supposed to give a vector instead of a list. Moreover, if we write down these arguments within the apply function with an additional numeric 1 argument, then we will get an error which is given here. Here the error reads all the latent things. If the function returns results of different types or lengths, the supply function will return a list as we have seen here. But under the similar circumstances, the apply function will give you an error. Now let us consider another aspect of these two functions. Suppose we have 3 vectors containing a large number of elements. These are vect, vect1 and vect2 as it had been defined here. Now we are putting these 3 within a list, and here is the list that we are coming up with. Now suppose we want to find the means of these 3 vectors at a time. So we are taking the help of these two functions, supply and apply. Since both are giving the same results, so now we are concentrating on the runtime of the two. So here if we use the system.time function, then we will have these results. From this, it is very clear that the time taken in case of supply function is much more than that of the apply function. Now just try to find what is happening here. The primary reason is that in case of the apply function, we are fixing the type of output that is needed to be returned. But thing is not like that in case of the apply function. So R itself needs to take decision on that. So this function is taking more time compared to the previous one due to this reason. Here one thing that I want to mention is that here indeed the time difference between these two functions are very few, but when it would be the case that we need to deal with a substantially large number of data, then we will surely be benefited by using this function. Here comes some of the ideas about the looping patterns. In this discussion, we will primarily notice that how these looping patterns are related with the arguments of the Laplace family of functions. Here you need to remember some of the basic ideas of looping over a vector. Three of these kinds. Firstly, the one considering the loop over the elements of a vector. Secondly, loop over the numeric indices, and the third one is loop over the names. Now let's take up the first form. Here we are considering a vector of length 100. Next, what we are doing is we are constructing a for loop where the loop is built over the elements. Here x is going along the elements of the vector vect, and then we are applying the square root function here, and we are ending up with the square root of the values. Often we do not come across such kinds of looping structures. Why this thing happens? Usually this is not a good choice because the way it saves the output is indeed very inefficient. With this form, it is very natural to save the output by extending a data structure like the one we have given here. This is slow because each time you extend the vector, R has to copy all of the existing elements, and many a times we often see that we should avoid copies more and more. So we are not interested in this method, at least for the for loop. Instead, create the space you will need for the output and then fill these. This mechanism is primarily used in the following type. So let's concentrate on this. Here we are looking at a for loop which primarily loops over indices. Like consider the one we have mentioned here. Here at first we are initializing the vector called val with the elements 0. Then with this index I, we are applying the function squared to each of the elements of the vector vect, and the output corresponding to each of the indices are stored with that index corresponding to the val vector. Here it is needless to say that this is the better way to deal with. Here you can always use sequence underscore along as well. So as we are seeing the number of ways of using the for loop, three basic ways are there for the Laplace function as well. The sequence of these are as it had been given here. So the question that arises is, will we prefer the second one as well compared to the first? The answer is no. We will not prefer that. We would use the first one because the Laplace function will take the responsibility to the output. So there is no need to worry about all these things. Then when do we use the second function or the third one? We will use them for knowing the position or name of the element that are involved. Both of them will give you the position and the value of the desired elements. So primarily this is all about Laplace and its subsidiary functions. Before starting to learn about the Laplace function, let us have a quick look about the Laplace function. In the course of advanced R,
you will come across ways of mastering the art of meta-programming and non-standard evaluation. Some discussions will be there regarding the use of environments. So, we are not going into the details of those things here, but here the thing I want to mention is that in many of the cases we do use environments as data structure because of some reasons. In our future modules, we will let you know how the objects are stored within an environment. But for the time being, let us consider an object is stored within an environment. Let us consider that. In that case, to use those objects and to define some functions with the help of these, we often use eApply function as a functional to the environment in case the object is stored within an environment. Now, let us see how it works. Here we are considering a new environment and we are naming it as env_new. Now, our next job is to define the elements of the environment. Let it be A and B. So, here as it had been shown, we are assigning the values of A and B with the help of these command that had been given here. Let the values be 25 and -22, it can be anything. So, 25 is the value of A and -22 is the value of B under this new environment. Now, suppose we want to write a function that whether the values under the new environment is positive or not. In this case, the use of the eApply function will make the whole work easy. Just have a look at the arguments within the eApply function. Using the conditional statement if else, we can surely determine which of the object is positive and which is negative within the environment.
So, as you have seen in this module, we had some primary discussion about how loops can be replaced through functionals. Here we had used some functionals like lapply, sapply, vapply and eApply functionals, which are basically higher dimensional functionals. And here with the help of some examples, we had shown you how these functionals are used. In the next module, we will show you the uses of the functionals like map function and lapply functions, and we will also give you some cases where functionals are not very well suited to replace the loops. So, let us see what is there in the next module.